Tarabunga is talking about magic condition in measurement-only circuits.
So, first of all, I would like to thank the organizers for inviting me to give this talk. So, in this talk, I would like to tell you about our recent work, which is about, so you can already see, so you already find an archive. So this is in a collaboration with Emmanuel Terito from ICTP, and this is about magic transition and measurement knowledge circuit. So this work is also part of a larger research effort to understand the behavior of magic in mathematical systems. And this is in particular in our group at ICTP, with my PhD advisor, Marcel Del Monte, and others. Okay, so first of all, I would like to introduce about magic. So this has already been done by Guillermo, but I think it will be useful to again rehash about this notion. So in particular, I would like to introduce it from the perspective of quantum circuits. So first of all, so the Clifford group is defined as the group of unitaries that map Pauli strings to Pauli strings. So Pauli strings is the tensor product of Pauli. So it is also known that it is generated by these three operators, Hadamard gate, phase gate, and control NOT gate, CNOT gate. And then Clifford circuit is defined as a circuit that contains only Clifford operations. Okay. So what is interesting about this Clifford circuits is that it is known by the Goetz-Markina theorem. It is already introduced, pointed out by Lorenzo that by the Goetz-Markina theorem, it is known that Clifford circuits can be simulated efficiently by the classical computer. And this fact is somehow maybe surprising at first because, in particular, Clifford circuits can be highly entangled. So this also goes to show that Clifford circuits, so it's like the entanglement is not enough to characterize quantum complexity, and we need another ingredient to introduce to sort of characterize complexity of the state. And what this also implies is that Clifford circuits is not enough to achieve universal quantum computation. In particular, Clifford circuits can only prepare a class of states called the stabilizer states, which does not encompass all three states. So in order to achieve universal quantum computation, it is known that it is enough to just add one gate, one non-Clifford gate, for example, the T gate. So the gate set of Clifford plus T is a universal gate set, so you can realize all possible states using this Clifford plus T gate state. So basically, we see that with only Clifford circuits, the circuit is classically simulable, not only by introducing magic, which is introduced by the non-Clifford or the T gates, that the circuit becomes universal and we can realize all possible states. So we can see that magic is a sort of quantum resource that allows us to achieve universal quantum computation. And you can see also that this is a resource that goes beyond entanglement, because you see that Clifford circuits can be highly entangled, but this is not enough, and we need magic to achieve the universality. And also we can see because Clifford circuits can only prepare stable states, then magic, also known as non-stabilizerness, also characterizes the distance from the set of stabilizer states. So what I would like to talk about related to this magic is the phenomenon of magic transition, and this is somehow related to, or somehow analogous to, entanglement transition that we can observe in monitor circuits. So again, I will review this for completeness. So the usual setup is like this, right? So we have the unitaries, which are and then there are the local Z measurement, which is also random, so it occurs at probability P on each side. So basically, the unitaries tend to increase the entanglement, and the measurements tend to decrease the entanglement. So we have the computation between the unitary dynamics and the measurements, and this computation is known to result to the transition of entanglement in terms of the scaling of the entanglement. So you can have entanglement phase where the entanglement grows as column, and we have the disentanglement phase where the entanglement grows as radar. And then what I would like to mention also is that in terms of the numerical simulations of disentanglement transition, it is common to use Clifford circuits to sort of perform large-scale simulations, because, as I mentioned, the Clifford circuits is efficiently simulable. So this allows us to reach really large system sizes. For example, here usually it can easily reach up to hundreds of qubits. And this way we can really see the different entanglement scaling, like the volume law, the random scaling, and the area law scaling. Also, so in several works, it has also been established that you don't even need the unitary dynamics to get this entanglement transition. So, in particular, even in circuits with only measurements, you can also observe entanglement transitions. Obviously, the measurements have to be non-commuting so that we still have non-trivial dynamics. And yeah, this some examples of the works that study this of course not complete. This has been established somehow. Okay, so what I would like to ask is whether or not there is a so what I would like to ask, no, please. Okay, sorry. So what I would like to ask is whether or not there is a corresponding magic transition in similar setup. However, there are some challenges if you want to study this magic transition. This is because, first of all, we lack efficient methods to simulate circuits with magic. So to compare with entanglement transition, so I have mentioned before that usually we can make use of Clifford circuits to simulate entanglement transition. But the problem is that Clifford circuits have no magic, so there is no non-trivial magic dynamics. We can, for example, introduce T-gates to Clifford circuits to induce magic, but in this case, there are no sort of efficient methods to simulate this kind of circuits. So this is one problem. And the second problem is that it is generally difficult to compute genuine magic measures. So we'll elaborate more on this point. So far there have been several measures that have been proposed, but the problem is that for most of these measures, it requires optimization to compute it, and the optimization is over the set of stable states, which grows super exponentially with the qubits. And because of this, usually in practice, we can only compute it to up to 5 qubits. So with this, we cannot answer questions about the behavior of magic in the systems. These are some examples of the measures. Of course, so recently there was a measure that was introduced by Lorenzo. It's called the symmetry entropy that Guglielmo has also discussed. And after this introduction, then it has now become possible to sort of study the behavior of magic in the systems. So I would like to mention just that we have proposed some methods to simulate to compute magic in large systems, particularly using tensor network methods. So in the first method, we do a Monte Carlo sampling with that type of tensor network called tensor network. Yeah. Basically, we just exploit the tree structure so that we can perform the sampling in with cost that is logarithmic in size. And then in the second method, we use MPS in the Pauli basis. So basically, we represent the state or MPS in the Pauli basis, which can be done by sort of tree. Then from this, we can compute the SRE using replica tree. There are of course other methods. There are other methods to compute the magic, also introduced by Guglielmo and others. Sorry, don't know what's maybe your connection. I don't know. And with these methods, we are able to study the behavior of magic in large systems. In particular, we have studied the behavior of magic around criticality. So these are just to show some examples of results that we can get using our methods. Okay, so coming back to magic transition, so actually this has also benefited from the recently developed methods. So this was studied in these two works first. And the setup that they considered is quite similar, which is the Clifford plus T circuit. So here, as usual, there are the random unitaries, which here are Clifford gates. And then there are the Z measurement, which is probability P. So these two are Clifford operations. But now we introduce T gates to introduce magic in it. Then this occurs with probability Q, but it is worth noting that this Q is much smaller than P. So the Q actually vanishes with the system side. And then they simulate these circuits, and then they found that there is a transition between form law magic and one magic. So this is quite similar to what has been observed for entanglement, for example. But still, there are some limitations of these studies. For example, actually, as this is also related to the studies that I mentioned earlier, that the simulated is not scalable. It scales exponentially with system size, and also it is not quantified by into like genuine magic measures. So now we try to study the magic transition in a different setup, which is a measurement only circuit. And I will show that in this setup we can overcome the limitations of the previous studies. So the starting point here is a circuit that was first studied in this paper by Lang and Bihler. Here there are only measurements, and there are two types of measurements. So there is the sigma x measurements, which occurs with probability P on each side, and then there is the sigma z measurements. This occurs for each pair of neighboring sites, and this occurs with rate 1 minus p for each pair of neighboring sites. And because these two are Pauli operators, then this circuit is a Clifford circuit, which can be efficiently simulated. So they studied this circuit in terms of their entanglement transitions, and they found that there is a transition between two phases with both with and allow entanglement. As you can show here, as you can see here, it's in particular there is also a logarithmic scaling at the critical point. Okay, so we modify the circuit to introduce magic in it. To do so, what we do is to rotate the sigma x operator. As you can see, along the z direction, generic theta, generic angle theta. So for generic theta now, this operator is not a Pauli operator. So then if you measure it, then this is a non-Clifford operation, right? But still, even though this is a non-Clifford circuit, we show that this is still efficiently simulable, because in particular, we can show that the state at any time is a tensor product of rotated blade, of a class of state that we call rotated blade clusters, or RBC. So this state has this form. So this B is classical bit, and this B bar is sort of classical bit that is obtained by bitwise splitting of the bit. There's space here, space phi. So you see that if phi is 0, for example, this will be just the usual Baire cluster of the JZ. But here we consider a generic angle, generic phi. So using this observation, we can show that the circuit can be simulated efficiently just by keeping track of basically the list of the Baire clusters, the list of the RBCs, which can be characterized using only by the list of the clusters and their angles. Okay, so not only that, we can also compute the magic of this circuit efficiently. So to see this, to compute the magic, we first consider the magic of a single RBC. So you can compute the magic by first applying a Clifford unitary, that was shown there. So if you apply that to an RBC, you will obtain a state that looks like this. So you can see that this is already a tensor product state of single qubit states. So the first qubit is a magic state because there is the phase there. There is non-trivial. But whereas the others are stable states, it can only be either 0 or 1. And then we can use the known fact that magic measure must be invariant under Clifford unitary, and also composition with stable states. And so we see that the magic of psi, which is an RBC, is equivalent to the magic of the first qubit here, which is a magic state. And this the magic of a single qubit state is of course very easy to compute, even if, let's say, the magic measure involves optimization in the definition. Okay, so then to compute the magic of a tensor product of RBCs, we can see that this is just equivalent to magic of a tensor product of single qubit states, single qubit magic states. Right? So at this point, we can impose some restriction. We can, in particular, use a magic measure M. It doesn't matter which measure. What matters is that it is additive for tensor product of qubit states. And actually, it is known that there are some measures that have this property. this for example to the semester extent, relative entropy of magic, semester entropy, and so on. Actually, what's interesting is that for some of these measures, like for example the semester extent or relative entropy of magic, the definition itself requires optimization. So it is actually very hard to compute for large systems. But in this case, using the activity, we can show that in this case, even for large systems, we can compute this efficiently in this. Okay, so that is sort of how. So using the additivity, we can show that the magic of the state is given just by the sum of the magic of the single qubit states, which corresponds each to each of the pair clusters. Okay, so in the following, we will also discuss consider some linear combination of magic. So here we consider quantities that we call mutual magic and topological magic, which are defined here. So these quantities are sort of motivated by the similar definitions for entanglement, like the mutual information and the topological entanglement entropy. So this is like the generalized topological entanglement entropy for 1D. So in this case, we can also show that we can compute each of these quantities efficiently. It's quite sort of so interesting because for these quantities, we will need to compute the magic of partitions, and partitions are mixed states. And usually the magic of mixed states is much more difficult to compute compared to pure states, in particular because there is no known measure for mixed states that is computable. But in this case, we can still efficiently compute it using the same analysis as partitions. But in this case, the magic can also be reduced to magic of single qubit states. Yeah, so we do that again. Yeah, so here we consider this kind of partitions. Okay, so now I will discuss the numerical results. Now I will start with the 1D case. So here we fix the theta, the angle of the rotation, to pi/4. And using the technique that I described before, then we can do some large-scale simulations of these circuits. In particular, we can reach large systems up to around 2000 qubits. And what we can see is that, so at any p larger than 0, then the magic itself is extensive, as you can see here. But you don't, just looking at the magic, you cannot see like any feature like the transition. But the transition can be seen by looking at the mutual magic just here. So you see that this looks very similar to the behavior of the entanglement for this circuit that I showed before. And in particular, we also find that the mutual magic seems to diverge logarithmically at the critical point, which you can see here. So this is again similar to the behavior of the entanglement at the critical point. Okay. Then we also look at the topological magic. So here we see that it takes a constant non-zero value for p smaller than zero. This is the symmetry broken phase. And it is 0 for p larger than pc, which is in the trivial phase. So this is again similar to the behavior of the topological entanglement entropy, but there is a difference in which the value here is not doesn't seem to be quantized. So for the entanglement, this would be 1 in this case, or it can be 1, but it is always integer. But here this is this is 0.5. And in principle, you can also get different values just by tuning the angles, different non-integer values. Okay, then we also have performed some finite size scaling. Here we obtain the data collapse in which we can extract the critical exponents, and this is also consistent with the value from percolation. Maybe I forgot to mention before that this circuit can be mapped to percolation, so we know the critical point and the critical exponents of the circuit. Good. So now we look at a slightly different scenario. So here, every time we measure the sigma x tilde, the rotated sigma x, which is with probability p, we then again choose randomly with probability q that the theta is equal to pi over 4, and then or it can be theta equal to 0 with probability 1 minus q. So this means that with probability q, the operation is a non-Clifford operation because this is now not a Pauli operator, but with probability 1 minus q, it is a Clifford operation because now the theta x is just the usual, sorry, the sigma x is just the usual Pauli operator. So now we set q equals to 2 over L. So the reason for this is that to sort of mimic the previous studies in which the rate of the non-Clifford operations occur at vanishing rate. So in the previous scenario, the non-Clifford operations occur at like finite rate with finite p. But now with q that there is vanishing with L, we see that it is now vanishing with L. So in this case, we find that now the two phases display O1 magic, so it is O1 magic everywhere. So this will be like the entanglement where it is O1 everywhere, but there's also a difference in this that it doesn't seem to be diverging at the critical point, unlike the entanglement. But still, if you look at the mutual magic, this can be used also to distinguish the two phases because it seems to play the role of an order parameter where it is 0 in one phase and non-zero in the other. And then we also look at the 2D case. So in 1D, the entanglement is sort of an area law, so you can simulate it with MPS, for example. But now in 2D, this is not simulable with MPS, but still, this is just to show that without technique, we can also simulate higher dimensional systems. So again, we look at the same scenarios as before. So here we set, as first we set theta equals to pi over 4. So it's the same scenario as before. Here we again see the similar behavior as in 1D. So it is form law magic everywhere for any non-zero p. And we can also look at a Lagrangian from the mutual magic, and it seems to diverge at the critical point, which is also consistent with the value from 3D percolation in this case. But here the mutual magic, as you can see that the mutual magic scales as area instead of logarithmically, but this is actually also consistent with the behavior of entanglement in critical 2D systems. So basically we find that both in 1D and 2D, the mutual magic scales similarly as the entanglement. And then the second scenario, we set again the Q, the previous Q, as equals to 2 over n. And again, we observe similar behavior as in 1D, so it is now O1 everywhere. And it seems to peak around the critical point. And also we look at the mutual magic, and it seems to play the role of an order parameter, so it's 0 in the trivial phase and non-zero in the other phase. Okay, so this is the conclusion. So we introduce a circuit, which is a measurement only circuit, which can be efficiently simulated, and which magic can be characterized efficiently. And we are able to perform large scale simulations both in 1D and 2D, and we uncover some rich behavior of the magic and its linear combinations. Yeah, this is, thank you for your attention. And
okay, any questions? Yes. Yeah.
So you always look at the bipartite. So it's like your magic. You look. It's like bipartite magic.
So the magic itself is a property of the full state.
Yeah. So what is your quantity? So it's also been lost when you.
So apart from the magic, I also consider this is the mutual magic. Okay,
Yeah,
so
why do you
for this
look
one,
at
for this one,
Why do you look at the mutual magic?
Because when we look at first just the magic, we find that it doesn't seem to have any feature, and then we try to find some linear combinations that there are also relevant for entanglement, for example, just to see if we can see the transition.
But the magical mixed state has a bit different with state with meaning, no, compared to states.
I mean, you can define the magic for both pure states and mixed states.
Yes.
So
but it doesn't have
I mean,
exactly the
you can define the stable state for mixed states, and then you can define how far the state is from this set of mixed stable states. But okay, this, as I mentioned, it's much more difficult to characterize for mixed states, and this is why this is a problem. For example, if you want to compute this quantity for generic effectivity state, this mutual magic, it will be very difficult to compute in a generic state if you want to use like a genuine monotone. This is why I mentioned that in this case we are able to do this in this particular setup.
Yes.
The first plot of just the magic, if you compute the derivative, I don't you think that you will see the critical point in the...
Do you mean this criticality?
Yeah, so no. No, it was a figure that you saw before, just in the previous question.
So,
Yeah, that one. There is.
yeah, I would think so. Even that if you look at the derivative, if there will be some features.
Like some susceptibility.
Yeah, I would think so, but it's somehow a bit more difficult because here we
Is
need
it
to
pretty
like
flat, right?
yeah. Yeah, but I believe that
I don't know.
So it should be something like this to have a peak in the derivative.
Yeah.
Secondary.
I think it's secondary.
Maybe second.
Maybe it's
Okay. Yes.
So, is your catch? I mean, what is actually the difference between entanglement and I mean, mutual information in general and mutual magic?
That's a good question. It is somehow okay. So for the mutual magic, let me just discuss the mutual magic first. So usually the magic itself is extensive with signal size, right? If you look at a generic state. Here if you look at the definition of mutual magic, this would cancel the volume law contribution. So the mutual magic, you can see that as a proxy of the first subleading contribution of the magic. Whereas this one, the topological magic, for example, it will give you the second order leading contribution because it cancels the volume and area law. Right. So it's like trying to tell us the subleading contributions of the magic. This is also true for entanglement, but not okay for the mutual information. It's not doesn't give you the subleading, but if you look at the topological magic, you can see the topological contributions of the entanglement.
So that, I mean, the topological magic does catch topological order, like
Yes.
but it's not universal kind of contract because it depends on the
Yeah.
Okay.
Can you somehow give an intuition in terms of if you have a circuit and now you just look at the unitary that connects A and B, how many T gates you have in that column of unitary, something like that.
I don't know, sorry.
So because I understand that somehow the mutual information tells you how much information you have between A and B, and somehow related to only those unitary that connect A with B and not. And so if you think of a quantum circuit, now you say A and B, and then there are gates in your quantum circuit that crosses the boundary between A and B, and then you could ask yourself how many T gates are in that column. Or imagine that you have just two of the unitary because you have a big one circuit or something like that. You can ask yourself how many T gates you have in that column. Could it be related to this?
I think that's a good question, but to be honest, I don't know. But I think it's one of the things that we would like to address. How this mutual magic really corresponds to that kind of quantum.
Okay. Any other questions?